Hello and welcome back. As promised, we are back with the discussion on improper integrals. So let me start sharing my slides and we will start with the very basic parts. We will see what is an improper integral and how to deal with them. So I hope you can see these slides by now. All right, so improper integrals, they exist or they come into our picture when either the function, the integrand, is unbounded or the interval over which we are considering the function, that interval is unbounded. Whenever any of these two happens, what we get is an improper integral. Okay. So the latter case, when the interval is unbounded, what may happen is that you may have some real number a, and then the interval may be open a, open infinity, or it may be closed a, open infinity. The other possibility is when you may have a real number b, which will be the right endpoint, and the left endpoint is the minus infinity. So minus infinity, open b, or minus infinity, closed b, or you may have the whole real line, which is minus infinity to infinity. So these are the possibilities. In either circumstance, what we have to do is that we have to modify our normal rules of integral approximation. We will have to properly define what we mean by any of this. So we are going to concentrate on one particular type of the improper integrals where the integrand is unbounded at the left endpoint. So we are assuming that our endpoints are bounded. We are looking at the real number a, real number b, and we have integral a to b of a function f where f is not bounded at a. That is the situation that we are going to consider. In fact, what happens is that every other improper integral can be reduced to problems of this form. So this is not really a special case, but it's a very general case. And whenever we have such a case where the integrand is unbounded on the left endpoint, we say that our function f has a singularity at the point a, at the endpoint a. So those are the functions which we are going to consider. A typical function will look like this. You have the interval a to b. At b, there is a finite value. Within the interval, there is a finite value. But as the variable x approaches a, the function shoots to infinity. This is a very typical situation. And now you have done your calculus courses and you would know that this particular improper integral, which is dx upon x minus a to the p, this is a typo, x minus a to the p, this will converge if and only if 0 less than p less than 1. Whenever p goes beyond 1, this integral doesn't converge. That is something that we know from our calculus course. And what we actually have is that this integration a to b x minus dx upon x minus a power p is obtained as a limit of capital M going to a from the positive side, and the limit of this x minus a power 1 minus p upon 1 minus p. This is why we are saying that it should be less than 1. And the limits are going to be taken from x equal to m to x equal to b. And the answer then is b minus a power 1 minus p upon 1 minus p. So this is the case what happens when you have dx upon x minus a power p. And for instance, this improper integral square root dx upon square root of x converges, and it will converge to 2. You can just look at the above formula and compute this particular integral where your a is 0 and b is 1. Whereas if you are looking with the same endpoints but the function is 1 upon x square, then its integration diverges. So some improper integrals do exist, they converge to a real number, and some other just go to infinity, they diverge. So we will have to concentrate on the ones which converge because those are the ones that we are going to approximate. Moreover, if you have fx equal to gx upon x minus a power p, where the limits on the p are the same and g is now a continuous function, then the corresponding improper integral does exist. This is again from the calculus course, and these kind of integrals will be approximated using the composite Simpsons rule. But to apply these composite Simpsons rules, you will have to take some set of nodes, and you will have to assume some continuity or continuously differentiability. And so we will assume that G is 5 times continuously differentiable, because then we will also be able to use the fourth Taylor polynomial, which is P4x, for the function G, which is the numerator of the integrand about A. So this Taylor polynomial will look like GA plus G prime A x minus A plus G double prime A upon 2 x minus A square plus G triple prime A upon 3 factorial x minus A cube plus the fourth derivative of G at A upon 4 factorial x minus A power 4. This is the fourth Taylor polynomial for the function G, which exists because we are assuming that G is 5 times continuously differentiable on AB. So this is what we have. We have this numerator G, which we are going to approximate by P4, and we want to compute integral of f. So there is this denominator which we have. So what we do is that this integration a to b fx dx, which is really integration of gx upon x minus a power p, we write it as sum of two integrands, where we have gx minus p4x upon x minus a power p plus the remaining part, which is integration of p4x upon x minus a power p. Now remember that p is less than 1, and p4x will start from constant, then linear, quadratic term, cubic term, and quartic term. So the integration of this second part can be computed quite easily. P4 is a polynomial after all, and that turns out to be this particular integral k going from 0 to 4, integral a to b. Each of the terms of P4 that we have, we will put them here, and the power of x will be k minus p. Okay, that's the only thing, and we can easily compute the integration, which will be summation k going from 0 to 4, the kth derivative of g at a, k factorial, and it's really the integration of x minus a power k minus p. That is k plus 1 minus p, b minus a power k plus 1 minus p. So the integration of the second part is computed quite easily, and now we have to compute the integration of the first part, but the second part is really the dominant portion, because p4x is the Taylor polynomial, and meaning what happens is that this Taylor polynomial approximates your function quite well in most of the cases. So whenever p4x agrees closely with the function gx throughout the interval ab, then the difference gx minus p4x is bounded by some uniform quantity over the integral ab, and therefore its integration is a smaller quantity. But anyway, we need to determine this integration, and what we then do is to use the composite Simpsons rule. But for that, we define a function which is capital G of x, which is given by the integrand gx minus p4x upon x minus a power p, where x is not equal to a. I have written a less than x less than or equal to b. So we are integrating it over the interval ab, but for the point a, x equal to a, I am defining my function capital G to be 0. And now this function is definitely continuous. In fact, it's more than continuous. We have that 0 is less than p less than 1, and p4 kth derivative at a agrees with the g kth derivative at a for k going from 0 to 4. So what we have is that g is actually 4 times continuously differentiable. So you can use Simpsons method, and you can easily compute the integration for this particular thing. You will have to compute the various values of g at various points within a and b, and write them with the corresponding coefficients. There will be some particular constant outside, and that will give you an approximate value using the composite Simpsons rule. You add that to the value that you had already obtained for the integral p4x upon x minus a power p, and you have an approximate answer for your integration of the function f. Okay, so I guess it's time to do an example. What we are going to do is to look at 0 to 1 e power x upon root x dx. So we have already observed that 1 upon root x dx integration from 0 to 1 converges, and e power x is a continuous function. It's continuously differentiable. In fact, it's a smooth function. So this integral exists. We will compute the P4. The polynomial P4 is 1 plus x square by 2 plus x cube by 3 factorial, which is x cube by 6 plus x to the 4 by 24. And therefore, the integration that we are looking for will have two parts: e power x minus p4x upon square root x dx, and then integration p4x upon square root x dx. So this integral actually is very easily obtainable because you have 1 divided by root x, so that gives you x power minus 1 by 2. Then you have x upon root x, which gives you x to the power 1 by 2, and so on. So you get all these um, polynomials, or a very well behaved functions, not really polynomials, rational function, and its integral can be obtained quite easily. Its approximate value is this: 2.923545. Let's say we ignore that 9, we round it up. So we have 2.923545. Okay, and then we have to look at the remaining part, which is the integral 0 to 1 capital Gx dx. Remember, capital Gx is defined in this way. The integration for capital Gx and the integration for the Gx minus p4x upon x minus a power p is the same, because the function capital Gx and the integrand, they differ only at one point. So this is something that you would have learnt in your calculus course, that changing the value at a single point does not change the value of the integral. So we have to just compute the integration from 0 to 1 of gx dx, and we use our Simpsons rule, which will tell you that this integral 0 to 1 gx dx is h by 3. H is the step size, which is 0.5. Then the endpoints g0 and g1, they come with multiplicity 1. The other even term, which is g 0.5, that comes with multiplicity 2. And the odd terms, which are x1 and x3, they come with multiplicity 4. So we have to just compute the value of this function capital G at these various endpoints. These are the values. I just have computed them for you. And the final answer turns out to be this 0.0017691. So we see that this part of the integration is really not as significant as the other part. So we add this to the other part, which you remember is 2.9292345. Okay, and then adding this part gives us the final integration value, which is 2.9253141. So we have computed this approximation to our improper integral, where the function has a singularity at the left endpoint A. Now what will happen if you have a singularity at B? What is indeed going to happen? If the integrand has a singularity at the right endpoint, you may develop a similar method of computing the approximate integral as we have done just now. So of course, we are assuming that the singularity is only at B and not at A, right? Then we could develop a similar technique, making appropriate changes to our earlier technique. But alternatively, what you may do is that you may apply the substitution z equal to minus x, which will give you dz equal to minus dx, and then the integral a to b fx dx is integral minus b to minus a f of minus z dz. Now a is less than b, and therefore when you multiply by minus 1, minus a is going to be bigger than minus b. And now this function f of minus z has a singularity at minus b, which is now a left endpoint. So we have converted our integral as an integral of a function over a different interval, actually of a different function altogether, which has now a singularity at the left endpoint. Now it may happen that you may have singularities at both the endpoints A and B, or you may have a singularity at some point in between C. So what we are going to do in that case is that, so let me complete this case first, that whenever you have converted your function which has singularity at B to a function which has a singularity at left endpoint, then you apply the previous techniques and the functions would look like this. Earlier you had a function defined on AB. Now you have a different function which is defined on minus B to minus A, and what you have done is just that you have obtained some kind of a rotation. If you are allowing your whole thing to revolve around the y-axis in the xz plane, then you have revolved the whole thing and gone to the negative side of the x-axis. That's what we have done. Okay, so if your integrand now has singularities at both the endpoints, or if it has a singularity at some point C between A and B, then the situation is actually quite simple. What you do is that you write the integrand A to B, the integral A to B as integral A to C plus the integral C to B. So if your function had singularities at A to B, A and B, and C is a point where the singularity doesn't exist, then you have written it as a function as a sum of two integrals where the singularity is at only one endpoint. The first one has a singularity at A, the second has a singularity at B, but you know how to convert it into again another integral of another function over a different interval which has a singularity at left endpoint. So you know how to deal with that case. If you have a singularity at C, then you write it as integral A to B is integral A to C plus integral C to B. Integral C to B is okay because your singularity is already at the left endpoint. Integral A to C is where the singularity is at the right endpoint, but then again you convert it into integration of a different function over a different interval where the singularity is at the left endpoint. So having developed all this machinery for the functions which have singularities at only left endpoint, we can take care of all these functions. Now the only case is where your interval itself might be unbounded. So let's look at that case. So the other type of improper integrals will involve infinite limits of integration. So the very basic integral of this type has the form integration a to infinity 1 upon x to the p dx, where now p is bigger than 1. What we then do is use the substitution. So t is x inverse, dt is minus x to the minus 2 upon into dx, which gives you that dx is minus x square dt, which is same as minus t to the minus 2 dt. We are assuming that a is not 0, because if a is 0, then you are not able to obtain anything, meaning if you have 0 to infinity and you apply x going to 1 upon x, you again get the interval to be 0 to infinity. So that is not really going to solve our problem. So we assume that a is non-zero. And so we have the integral a to infinity, which is same as integration 1 upon a to 0, because you have substituted that x going to t inverse. And because your a is assumed to be positive, you have finally integration 0 to 1 upon a, 1 upon t to the minus 2 minus p dt. And in fact, if you have any such function which is defined on a infinity, then we apply this substitution and obtain integral a to infinity fx dx is integration 0 to 1 upon a t to the minus 2 f of 1 by t dt. So this is how you would work with if your right endpoint is infinity and 0 to 1 upon a is a finite interval. You have a very well behaved function and you can compute its integration there. If your a happens to be 0 or both the endpoints are infinite, then we do the similar trick that you insert a point C and you write your integration a to b as integration a to c plus integration c to b fx dx. So it's a very simple trick that we are going to use almost always to convert very difficult types of proper integrals to the types of improper integrals that we have seen and studied quite a lot. So I'm very happy to announce that with this, we have come to the end of our fourth theme. Remember, we have 8 themes, and the remaining 4 themes are basically ordinary differential equations. So this is one theme. And then there are 3 more themes which really constitute numerical linear algebra. This is lecture number 28, which is also roughly the half of the total number of lectures that we are going to have in this course. So 28 more lectures to come, 4 more themes to come, where we are going to apply all the methods that we have learned so far. So don't go anywhere, stay on, and see you soon. Thank you very much.